When the protons enter the magnetic field, they're going to move on a circular path, and they've got to move all the way up to the detector. So this path drawn should be a neater circle than what I've just drawn, and also the force should be a right angle to the path at any one time, showing it's a centripetal force, and that's obviously labelled F. The direction of the field causing this motion, if we use Fleming's left-hand rule, the current is in the direction of the positive charge. We've got current going that way. When it first goes into the field, the force is at a right angle to that movement there. So on the left hand, the thumb is pointing up the page, the middle finger for current is pointing to the right, and my first finger for the field is pointing into the page. So the magnitude of the force on the proton is calculated from F equals B QV. It tells us that B is 0.50 Teslas. It's a proton, so the charge on it is 1.6 times 10 to the minus 19 coulombs, and its velocity, it tells us, is 5 times 10 to the 6. If we multiply those three numbers together, we get 4 times 10 to the minus 13 newtons. In part D, if the path of that of an electron with the same velocity, what two changes would need to be made to the magnetic field? Well, if it's an electron, it has the opposite charge, so it's as if current were flowing in the opposite direction, and the curvature would be in the opposite direction too. So the direction needs to be changed, so I would say reverse the direction. The other property of the electron compared to the proton is that an electron is much lighter, so it will curve a lot more. So the strength of the field would need to be reduced. So reduce the strength of the B field.